Yeah, so today I'm going to talk about dApps under the hood. So I'm sure you guys have written like a beautiful rough code that is elegant, function rich, secure, and everything just as beautiful as this watch. So basically today agenda, in the next 30 minutes, is to basically flip the watch and look at all the mechanics and the gears and everything from the see-through key stack. So basically how your smart contract is kind of converted into like a bytecode, and how does the transaction look like, and how does a VM actually execute the bytecode and so on. So here is an example of some beautiful rough code that I just took straight away from our documentation site. And this actually is executable. You can basically clone the code from the documentation. And I think this particular example is called your NFT, your first NFTs. So just a few words about the NFTs on Alephium, so that we are on the same page. So so typically, if we want to implement an NFT on Alephium, we need to have this NFT contract, which implements this interface called INFT, which allows basically the wallets and dApps to, for example, get the metadata of the NFTs and get its collection and so on. We also need an NFT collection contract. In this case, it's called also NFT collection contract. That also needs to implement an interface called the INFT collection interface. This is also useful for wallets and dApps and explorers to get the metadata for the collection, to display the images and so on and so forth. But probably the most interesting function in this NFT collection contract is this mint function, because we obviously want to mint new NFTs. Yeah, one thing that so basically the way that we sort of mint an NFT on Alephium is typically to create something called subcontract. So in this mint function, we will create a NFT contract instance as a subcontract of the NFT collection contract, basically. So for all the collections, for all the NFTs under this NFT collection, they're all the subcontracts of this NFT collection. So this is basically like a typical way of implementing like NFTs on Alephium. Yeah, and when we create the subcontract, there's like two ways to do it. One is to basically use the contract bytecode. And this is quite useful if you just create the contract the first time, or you just want to just create a contract. You don't want to create more of the same contract. Another way is to do something called a copy create contract or copy create subcontract, which basically you need some kind of a pattern there to create a dummy like a contract first, and then passing the contract ID of this dummy contract as kind of a template, and then you can create more of the similar contract in a more gas efficient way. And obviously, in the NFT collection case, we want to create like many NFTs. They share pretty much the same code, so we use the second approach. So we're passing this NFT template ID. Yeah, so that's pretty much the context for this example. So once we have this contract, the next thing we can do is to so assume that we all know how to compile this contract. So basically, the SDK after compilation, it'll generate a corresponding TypeScript like a class for each of the contracts. So we had an awesome NFT contract, then we'll have an awesome NFT TypeScript class, which exposes a method called deploy, and then we can basically deploy this. And this will return a contract instance, basically reference the contract, and also this will basically submit a transaction. So you will have a transaction ID as well. And then once we have, so this is a dummy one, dummy NFT contract. So after that, will take the contract ID for this awesome NFT, treat it as a template, pass it into this NFT collection contract. Then we basically deploy this NFT collection contract. So after this NFT collection contract is created, the next step, we can basically start to mint. And this is again, this example is in the documentation side. So if you want to like clone the code and experiment it, it's like 50 lines of code to basically create your first awesome NFT. So a question for you guys. So we all know that we can like do a transfer on Alephium, and we can sort of execute a script, like a transaction script on Alephium. So like there's two transaction types. One is to just do a pure transfer. Another one is to execute a script. So do you know like what happens if you just call deploy here? Do we have like a third transaction type called a deploy? Like because on endpoint there's a contract deploy endpoint, so you can basically call and deploy a contract. Anyone knows?
Speak a bit louder because
Oh, okay. Yeah, sorry. Yeah, so my question is, any of you know like what's happening under the hood if we actually call the deploy function for example, the awesome NFT contract? Okay. Okay, we all learn something new today. So what actually under the, so there's only two types of transactions on Alephium. One is to basically do a normal transfer. So if you just want to transfer some assets from one party to the other, that's like a normal kind of transfer transaction. And the second one is like when you try to interact with the with a VM, with the contract and so on. So in this case, it's actually falls under the second category. So when you call deploy, what happens is that on the backend, it's automatically going to generate this transaction script, which calls this function called create contract. This is like a built-in function, and it takes like the contract bytecode and also the initial like the fields that you want to initialize this contract with. So in this particular case, when we try to deploy the awesome NFT contract, it's actually, yeah, it pre-fills all these fields with proper value. So this at thing is the whoever is trying to create this contract, and this start with 04, that's actually the bytecode for this awesome NFT contract. And then the next two fields, the first one is the mutable field, like immutable, encoded immutable fields. And the second one is like immutable, encoded mutable fields for this contract, because you can define for each of the fields, you can define them as either mutable or immutable, and this is actually separated out at the VM level, so it's like maintains higher. It's easier to maintain higher security for that and more efficient. So this is what I tell you, right? And you don't need to believe me, but we can basically take a look at the transaction, like dive into the transaction and see how the transaction for deploying this awesome NFT contract looks like, and yeah, try to understand whether this is the case. But before that, maybe just a few words about the transaction sort of data type. So this is how the transaction looks like, the unsigned transaction looks like on Alephium. So it has a few fields. One is the version, which allows for like a future evolution of the data structure. You have like a network ID, which right now has three values: mainnet, testnet, and devnet. You have guess related fields, which is quite common for like if you have a background in other chains. And also like inputs and outputs, which is a very typical like thing for a UTXO based chain. What's kind of unique for Alephium is that there's this optional like a script field, which contains like a bunch of bytecodes for like interacting with the chain. Like you can express a bunch of stuff. This is basically where the stateful UTXO model like manifested itself into in this like a transaction data structure. When you execute when we execute this transaction, the script can potentially invoke like a transfer assets between like the contracts, and it can potentially generates outputs like a transfer, for example, like some alpha to some recipients, right? So when we like finished executing this transaction, there's like a couple of more fields. For example, the contract inputs is like when you try to get so when you need the assets from some contracts, you do that, and then you can like generate a bunch of outputs from the execution of the scripts, and then you have that. You need obviously you need a bunch of signatures. So once the transaction is executed and properly signed, the data structure look something like this. So let's take a look at this in. Okay, your keyboard is a little bit different.
Swiss keyboard.
Do you have a Z here?
It's inverted with Y. Y.
Okay. So the transaction ID for creating this awesome NFT contract is this. So there's this tool that we can use to basically. Okay, copy paste doesn't work.
You have to do it with it's the other one. So it's this one. It's not control.
Okay.
It's this.
All right.
There we go.
Okay, so this is so remember I mentioned the data structure for the transaction, right? So you have version, network ID, scripts, and blah blah blah. And here you can basically see the serialized version of the transaction like over the while, but it's highlighted based on like which bytes actually is represent what, basically all the fields and so on. So for example, this is a version which is 0, and this is network ID, and this whole bunch of things is actually the bytecode for the script. Yeah, and we have guess amount and so on. So you got the idea. So basically, this is a like colorized version of the transaction. So you have this breakdown, basically tells you exactly what those things are, what those things mean, right? You can basically make the connection between this data structure and this page. So going back to our question is that after we call the deploy, is this TX script the thing that is actually executed, right? So this thing. So to be able to do that, I think we need to understand a little bit more of the sort of the opcode. So in this breakdown page, when we look at the script, it actually already tried to colorize all these like a bytecode to sort of suggest what it means. For example, here you can see like this is the address const, and this is yeah, things like this. But let's go back to the presentation itself. So all the scripts, so all the like rough code and TS script and contracts are converted to this bytecode that is colorized here, like script opt, basically. And how do we execute that? So I'll give you a simple example first. So let's say we have something like this. These are all valid opcodes. You have like U256 const 1, and yeah, const 0, and we have Boolean equal. And then we have U256 const 0 again. And then we have a byte opcode called assert with error code. So when we execute it, it looks something like this. So first we run U256 const 1, and then this basically does nothing but push this thing into the op stack. And then the next thing is another const. We push it again into the op stack. And the third one is Boolean equal. And obviously these two things on the stack is not the same, right? So this is going to return like a const false. And then we push like U256 0 again. So this is going to be stacked on top of the stack. And then we run this assert with error code. As you can see, this is a failure, right? Because it's a false there. And then the error code is going to be 0. So this is basically the converted bytecode for this very simple statement: asserts 1 equals 0 0. And then we have like more opcodes, such as like address const, which basically just push the address into the stack. And yeah, the numbers, the bytes, the bytes. And also we have this very interesting opcode called approve auth. So we are talking about like asset permission system and all that, but under the hood is actually we actually do have a opcode called approve auth. So for example, when you try to approve a certain amount of auth in the function, this is what's underneath it. So each of these like opcode has some kind of a semantic, right? It assumes that certain stuff are on the stack, and then when it tries to execute it, it expects, for example, for approve auth, it'll expect a address to be in the stack, and also the amount to be in the stack. So when it executes it knows like who actually approves what, like in the VM, right? Yeah, and then we have, for example, like a bytecode, like opcode for create a contract, and then we have bytecode to pop stuff from the stack. So with this, we can already try to. So there's this new tab called replay. So remember, this is the transaction that we use to deploy the awesome NFT contracts, right? So in this replay, we can replay this transaction. As you can see, the first one is a address const, which what it does is to basically push the address into the stack. As you can see here, this is the address. So this is the op stack. Let's go back to the code here. So basically, this will push this address first into the stack, right? And then the next thing is this number. This number is encoded using something called a compact integer like encoding. You'll see that this is actually the 0.1 alph here. So this is basically this part. So it pushes this as a address, and it pushes this as a number, right? And then the next thing they push is next thing they execute is approve auth, which takes these two things in the stack and try to approve certain amounts of alpha, like 0.1 alpha, for the next function, basically, so, which like in the VM is called frame. So if you execute this approve alpha, it's not displayed, but like you can imagine, like in the frame, it gets the allocation of 0.1 alpha, and that's all basically is authorized for this frame, and it couldn't. Yeah.
How does it know it's alpha and not some other token?
It's because this opcode is called approve auth, and there's like approve token. It's like, there's other like opcodes for other tokens, and then you probably will expect the token ID in the stack. So after we approve this, so what's next? We will push this into the stack, because this is just it's just array of some bytes, and this is actually the bytecode, right? So if you compile the awesome NFT, you will see. Actually, okay, I don't have the, but if you compile the code, if you remember, there's this JSON file, and you can see the bytecode of this contract in the JSON file, and this is basically the bytecode for awesome NFT contract, and then this is the immutable, like encoded immutable like fields for this awesome NFT contract, and this is the mutable encoded fields. And then basically we call the create contract, because it expects like the bytecode for the contract, and then you expect the initialization like fields for this contract. When you call the create contract, it will basically create a contract in the VM. So that's how it, and then it returns like the contract ID of the newly created contract, and then you pop it and return, and that's basically how the deploy like works under the hood. So that's yeah. So I didn't lie to you. It's basically just this, right? So now we have explained the deploy, and the next thing is to mint, is to call the mint function. And before we do that, there's some more stuff that we need to say before that, because for us to call, so the previous example, we don't actually interact with the contract, but if we want to interact with the contract in the transaction script, we will have to create something called like a frame, like in the VM, like when you invoke a method, normally it creates a frame, and then if this method calls another method, you basically create another frame and put it on top of the frame stock. And then when you finish executing this method, you basically pop the current frame out, and then you execute the next frame. That's basically how we call methods. So it's the same with the Alfred VM. Okay, so there are like a few more instructions that we, yeah. So there's like a few more instructions. We can probably like finish this before we get into the contract interaction. But like for example, there are, if you remember, there's like this caller address built-in function, and that has a corresponding like opcode. There's also like a self contract ID built-in function that has this own opcode as well, and there's like return opcode, encode, like you can add the U256, and you can also, yeah, this is the opcode to create a subcontract, and then like issue certain amount of token and then transfer it to some kind of a recipient. There's one opcode specific for that. So I just talked about like the frame stack. So to be able to like call a contract method, there's like specific opcode for that. So you can call like external, and you can have like a contract ID in the stack, and this one actually has a method index, so you know exactly which method are you calling. You can also call a local function, which you need to like basically have this method index in the stack as well. And then in the Room upgrade, we have introduced this new opcode to select method based on their like signature hash. So this is a new opcode. And then for each of the frame, like in the method, we have a few things that we keep track of. For example, like the number of local variables in this method. We maintain like something called a local stack to keep track of that. And also for each of the contract, there's a state, right? Because you have fields and you have like immutable and mutable like fields, and for mutable ones you can basically read it and write it and so on. For the immutable ones you can read them. So there's just like a opcode to do that as well. So for the contract, we if we look at the contract, for example, the awesome NFT contract that we just created, we can use we can take a look at the contract bytecode to understand like where do we actually put these bytecodes, because we want to invoke the method for contract, right? And we want to understand like how contract actually organize all those methods and where do we put all those bytecodes and so on. So here we have an address that we created for the awesome NFT contract. And this is basically the bytecode that we have for that contract. It's actually the same. So it's actually the same as the one that we saw in here, because this is the bytecode that we use for creating this contract. So as we can see here, this is also highlighted with what bytes are responsible for what. If you break it down, you can see that first it has like information about like how many fields does this contract have, and it also has like a bunch of method indexes, which allows us to find like the methods. In this case, it has two methods. So like awesome NFT contract has like gets collection URL, and also it has a method to get the collection ID and index. So we have two methods here, and for each of the method we have a bunch of bytecodes here. So it has, for example, whether this method is public and whether depending on like what kind of annotation you have there, you encode, for example, like you can specify pre-approved like assets and like assets in contract. Those kind of annotation is encoded in the asset modifier. You encode, for example, the argument length and the return, the locals length, and the returns length, and then it follows by a bunch of like opcodes for this particular contract. So all this is to build up to like how we basically call this mint function in the NFT collection contract. Because if we look at the NFT collection contract, let's see. So this is the NFT contract. So this one is actually the NFT collection contract. As you can see, the bytecode is a little bit bigger, and if you remember, let's so let's find this this contract. So this is the contract that we are looking at. So it has this mint function, right? And all in all, it has 1, 2, 3, 4, 5 functions. So as you can see here, the decoded one has like 5 functions, and the fourth one is actually the mint function. So the min function has a bunch of bytecodes here. We will try to execute them like one by one to basically match the code here and see whether they make sense. But as you can see, we have like a bunch of codes here. It's like yeah, local and these things. For example, here it must have loaded some like mutable fields from the contract and so on. Yeah. So let's try to execute this. Okay, is this the? It doesn't have the replay. Okay, yeah. So this is the transaction ID for minting a NFT. And this is the transaction script that we use to mint the NFT, which is pretty much this one. This one. So we basically use the awesome NFT collection. We use that contract and try to call the mint function, right? And the mint function is the as we can see from here, is the fourth. Yeah, as we can see from the previous, because I just changed it to the transaction. It's the fourth method in the collection, NFT collection contract. So when we try to like execute this this transaction, we play it. First, it calls this call address built-in function, right? And it has a corresponding like call address bytecode. So you go here, and then it tries to push a certain amount of alpha into the stack, and it tries to approve it, which is which is basically here. We try to approve this much alpha, like when we mint the NFT, right? And then we try to push this arrays into the stack. And this is actually because when we mint the NFT, we specify the NFT URL. It's like HTTP, like this URL that points to the metadata of the NFT, and this byte is actually the URL, like HTTP URL for the NFT, the new NFT. And then we push like one, which is like when we create this yeah. Let me see.
The element of the collection, maybe?
Oh yeah. So this is some special thing for like calling an external like method, because for when we call an external method, we know the number of arguments that it takes, and also the number of return values that it takes. So the VM has some kind of a security protection for that. So this actually represents the number of like inputs, like arguments for the min function. And then the other one is the return value for the min function. And then we push in the contract ID for the collection, for the NFT collection. And then we have this call external like opcode that calls the number 4, so actually the fifth method of the NFT collection. So now, as you can see from here, the frame stack got this new like NFT collection like address popped on top, so which means that right now we are actually at the new frame that executes this mint function. All these bytecodes are actually part of the mint function. So this mint function, as you can see from here, it calls this call address built-in function first. So this is the first thing. Okay, so first one is actually a method selector. This is actually also a new thing that we introduced in Rune upgrade. Previously, we can only identify like a method based on index. Right now, you can try to find a method based on the hash of the method signature, and this is basically something in the bytecode to allow us to find which method we're calling. And this basically doesn't do anything. It's just a placeholder. So this doesn't do anything. And the next, the thing that actually does things, the first one is actually the call address built-in function, which has a corresponding like opcode call address, so which push this address to the stack, right? And then we just go we just move on to the next, which is like a self-contract ID, and then actually, sorry, it actually stores this caller address into a temporary variable, like a local variable, right? So the next one is actually to store local, to push it into a local stack. So basically, here you can see that this is actually stored here. We have 5 locals that we keep track of in this method when we execute this method, and this is actually pushed to the first local variable. And then after this we execute the self contract ID. As we can see from here. And then we load the mutable fields 0, which is the total supply. As we can see from here, the total supply, we have like 3 fields, and total supply is the first one. So we basically load the first mutable field, and this one will push things into the stack. And since this is the first NFT, it's going to be 0. And then we load the first local variable to the stack, which is basically the the URL, the NFT URL, because this is actually the parameter, and that's one of the local variables. So now we are at this point, right? And then we basically, what do we do next? We are trying to encode all the immutable, like all the mutable fields for. So we call this encode fields, and this one basically does 2 things. One is to encode all the immutable fields for this contract. Another one is to encode all the mutable fields for this contract. So basically, we have these two encode, as you can see here. One encode, another encode. We basically encode all the fields, and now we have 2 encoded immutable and mutable fields in the stack. And then we want to load a bunch of other things that we need to create a subcontract for this NFT, right? Because minting an NFT is basically creating a subcontract for this NFT collection. So we load some local variables that we have stored before. And also, we did the same thing by proving some ELF, because when we create this subcontract, we need some ELF in it to pay for the contract deposit. Anyways, if you follow this follow the next, ultimately you will reach to this opcode, which is to create a subcontract and transfer token. And by this point, you will have all the information in the stack already. For example, you will create one token for this new contract, which is kind of natural because NFT has only one token. You have all the like initial states for this contract. So once you invoke this thing, you will basically done with creating this minting this new contract. And then after, there's some other details. Basically, you store this into the results of this new contract ID into a local variable. That's why you see like store local and things like that. But ultimately, it finished like calling this function, executing all the opcode, and then it returns this back to the TS script. So it pops the method frame for the collection mint function, and it returns back to the TS script. And then here is where basically everything is finished. So now after this point, we have already minted this new NFT with like tokens and everything. Yeah, it's a little bit heavy. So but this is basically how opcodes are executed, how your like contract is like executed at a VM level. I think this is actually all that I have. So thanks a lot. And if you have any questions, I'm happy to take it. Hi, please.
I remember reading in a Medium article that something about NFTs cannot be sent from shard to shard.
Yeah.
Is that the situation still? What's happening with that?
So there's like two things, parts. One part is the token. Token can be like transferred anywhere, yeah. But the contract itself, which has information that points to, for example, the metadata and so on, those are fixed to a particular group. Please. Yeah.
So there are those storage options, and normally on Ethereum those are quite expensive. How does this compare here? Do you have maybe a number of how much you could pay, for example, to store an address in a contract?
I don't have it on top of my mind, but I think all the gas, like a calculation, I think we take pretty heavy influence from Ethereum, if I understand correctly, right?
We are much more efficient than Ethereum because the storage model is very different. In Ethereum, actually, every data is a record of 32 bytes. So a lot of smart contracts have a lot of server records. They need a lot much more read and write in the I/O level. In our case, it's different. We have a separate contract system. For each contract, we just have a single, actually two pieces of data need to be stored. And when in the execution of the broken transactions, all of the load and the store operations are actually done in the memory. And only when the execution is finished and completed, the changes are flashed to the database. Overall, it's much more efficient. I think for EVM, in the latest versions, they introduced something similar, but because of this storage model is fundamentally efficient, they cannot improve, optimize too much. So from the very beginning, we see the issue. We design it very differently. We try to make it very efficient, much more efficient. We did a comparison on the gas cost for the Uniswap V2. I don't remember exactly the numbers, but I think we are like only use 50% of the gas in Uniswap. So definitely much more efficient. Okay, thanks.
All right. Any more questions? Please.
Can you remind me what's the difference between a contract and a transaction script?
The transaction script. So contract is almost like a object, like in object-oriented kind of world. So it has its own states. it has a set of methods that you can interact with it. Transaction script is like a one-off kind of. It's almost like a bash script, but it's for transactions. So you can basically use it to initiate a interaction with a contract. You can probably like combine the interaction with like call multiple contracts and combine the results and something like that. So it's like more like a one-off thing, and you can, yeah. So this is actually quite a unique thing for Alephium, because if you want to do similar things like combine multiple multiple like contract calls and do some stuff to it, you will probably have to deploy a proxy contract, like a temporary contract to do that. For example, on Ethereum, but on Alephium you can actually write that logic in a transaction script. More questions?
Yeah. In the decoder, I saw that in the TX script options, there were two options, either 0 or 1, but they were both explained to be TX script. 0 means TX script, and 1 means TX script. So I was wondering if that's a...
You mean in the script opt?
Yeah.
So 0 means that there's no scripts.
Okay.
Yeah, it means that there's no. But if it's 1, then it follows by the bytecode for the script.
Okay.
More questions? All right, thank you very much, and have a nice lunch.